Okay, so good afternoon. Welcome to my channel. And today we are going to talk about the Doppler physics. We know from the history that this gentleman here, Christian Doppler, studied the behavior of stars, and he came up with the Doppler phenomenon. So what this gentleman did was to place musicians on wagons, then standing at a certain observation point. So he noticed that as the wagons or the train was moving towards his position, the frequency of sound coming from the trumpets was increasing. And the moment the wagons, which had the musicians with trumpets, passed him, the frequency of the sound reduced. So this is the birth of the Doppler phenomenon. For example, when you look at an ambulance, once the ambulance is approaching an observer, the frequency of sound increases. And the moment it actually moves away from the observer, the sound frequency reduces. So this is all about the phenomena of Doppler. So as we can see in this cartoon, first there must be a sound source, which is this one. This one is a transducer or a probe, and these are red blood cells. So the sound source in this case is the probe or the transducer. Then the receiver are millions of red blood cells in our bodies. So as the cells are moving towards the probe, the frequency of the sound, Doppler frequency, increases. But when they move away from the sound source, which is the transducer in this case, the frequency reduces. Yeah, so that's in short, the definition of Doppler frequency. It's a change in measured frequency due to motion between source and the receiver. Closer to the probe, there is a positive Doppler frequency, and further apart, there is a negative Doppler frequency. And we know the units of frequency, they are hertz, which are cycles per second. Typical value, 20 to 20,000 hertz. This is audible sound that we can hear with our human ear. But transducers usually have high frequency between 2 to 10 megahertz. So Doppler shift rides on the top of high frequency sound beam and is extracted by a process called modulation. So that's the Doppler equation, which is not really complex. So we know that Doppler shift is directly related to red blood cell speed, transducer frequency, the cosine, that is the angle of insonation, and the Doppler shift inversely related to speed of sound in the media. So how does blood flow in the heart? So in the heart, there are types of blood flow. We talk about laminar flow, which is smooth flow without any turbulence. We have also what we call turbulent flow. So that's chaotic type of flow in the blood or in the blood vessel in the heart. Then we have vortex flow, which is like tornado. So that's a spiral motion of fluid flow. So laminar flow has to be normal velocity. That is, the maximum velocity is between 1.5 meters per second. So this is a non-turbulent motion of fluid in which parallel layers have different velocities but relative to each other. Now turbulent flow, usually is high velocity because there is an obstruction. So what happens with flow dynamics? So flow to pass through a narrowed orifice has to accelerate. So that acceleration increases the velocity. So this is applied in stenotic lesions like mitral stenosis, aortic stenosis, and other vascular stenosis. Okay, that's spiral. The spiral type of flow is where the motion of fluid within a limited area appears spiral. So this is how blood flows in the heart. So it will enter the left atrium, then go laterally towards the wall of the left ventricle, and when it reaches the apex, it will turn round into the aorta through the aortic valve. So this is how blood flows in the heart. So when you put Doppler, color Doppler there, you see that the red flow towards the probe will go laterally, and the blue flow will turn as the flow now flows away from the probe or the transducer. So how many types of Doppler do we know? There's continuous wave Doppler. In continuous wave Doppler, there are two crystals. One is sending and one is receiving. So there's continuous, the crystal is continuously talking and the other one is continuously receiving. So this is a good modality for measuring high velocities. So for diseased flow, we use continuous wave Doppler. So this is where we can also apply to measure continuous wave Doppler in a case of aortic insufficiency. So these are the continuous wave Doppler applications. We can apply it on a VSD, ventricular septal defect, on the left ventricle outflow tract obstruction, aortic regurgitation. We can also apply continuous wave Doppler on aortic stenosis. We can also apply continuous wave Doppler on tricuspid stenosis. Wherever there is a diseased flow, we are advised to use continuous wave Doppler because it measures high velocities. There is no range ambiguity. So these are the gradients in the heart. So we know that we have the valves there and Doppler signal representation. So positive flow is above the baseline, negative flow is below the baseline. Now we come to another modality which is called pulse wave Doppler. Pulse wave Doppler measured velocities at a certain location, at a certain point. That is the advantage. So usually there is a source, which is the transducer, and the receiver, which is the blood vessel with red blood cells. So it has one signal, one crystal sending the pulse, then it will wait for a return signal. So for this one, the disadvantage, you cannot measure high velocities. So this one is for normal flow. For normal flow, we use pulse wave Doppler. So this is a presentation of the pulse wave Doppler at the mitral inflow signal, and it shows positive flow above the baseline and negative flow below the baseline. This is the four chamber view when we're doing an echo. Okay, so maximum velocity of pulse of Doppler depends on the imaging frequency, the pulse repetition frequency, the depth, and the site of the sample volume. So this aliasing occurs when the Nyquist limit has been reached. That means the flow or the velocity is beyond the Nyquist limit. So the Nyquist limit is the maximum velocity that can be measured by pulse wave Doppler. Okay. So pulse wave Doppler, okay, is great to determine where we want to measure. But the problem is it cannot measure velocities above 2 meters per second. So in this view, we need to switch to continuous wave Doppler. Okay, pulse wave Doppler applications: normal flow, mitral valve inflow, left ventricle outflow tract, pulmonary veins, tricuspid valve. Interrogation: normal flow. Okay, so we can also apply pulse wave Doppler at the pulmonic valve, hepatic veins, descending thoracic aorta. We don't expect high flow velocities there, so we actually use pulse wave Doppler. This is not diseased flow. Okay, Continuous wave Doppler applications, again, you can measure it, you can use it in pulmonic stenosis coarctation, where there's narrowing. So where there's disease flow, we expect high velocities. So we engage continuous wave Doppler. Color flow Doppler is directional. So it depends on the flow of blood. If the flow is towards the transducer, the color will be red, and the flow away from the transducer, the color will be blue. So this is how it represents. So blue flow, and always we look at the color bar box on the machine. So the red tells you that flow is towards the probe or the transducer, and blue is away from the transducer. So it's directional. So red towards the transducer and blue away from the transducer. So the color maps that we find on our machines. Okay, we come to another modality which is called color power Doppler. This one is angio. It's almost like an angio, color angio. It's good for interrogating very small blood vessels in the peripheries. Okay, we pass back. So another modality that we use in Doppler, in this overview of Doppler, is tissue velocity imaging, or tissue Doppler. So tissue Doppler is the Doppler signal of tissue. So it filters the high velocities of the red blood cells and only highlights the myocardium. So again, the color phenomena applies, red towards the probe and blue away from the motion of myocardium, of muscle or tissue away from the transducer. It's good for determining diastolic function and also looking at systolic function, especially the right ventricular systolic function. Okay, so what are jets in the heart? So jets are disease flow. Like in this picture here, we see this is an esophageal echo representation of mitral regurgitation. And every jet has got components. It has a jet body, vena contractor, flow convergence zone. So the jet body will tell us also how severe the regurgitation is, or the size of the flow convergence zone. Okay, we move to this gentleman. This gentleman is Daniel Bernoulli. Daniel Bernoulli was born in 1700 and died in 1782. So he lived for 82 years. So he came out with this Bernoulli equation. Looks rather complex, but it has been simplified for cardiologists. So we have a simplified version which says pressure gradient is equal to 4 multiplied by velocity squared. So when you get your velocity, you just multiply it, square it, and multiply by 4, you get your pressure gradient. And these formulas are usually embedded on the machines. So where do we apply the Bernoulli equation? On the stenotic lesions, VSD, that is ventricular septal defect, and assessing pulmonary arterial pressures. So we use Bernoulli equation to look at these gradients in these sites in the heart, that is the mitral valve, the left ventricle outflow tract, the tricuspid valve, and the VSD. There's an issue of PISA as well, although not really commonly used, but it's better to notice that PISA is all about flow acceleration. So these are the velocities that we find in the heart. Aortic stenosis, there's a narrowing, we find high velocity because here flow has to accelerate. Mitral stenosis, pulmonary stenosis, aortic regurg, mitral regurgitation, VSD, especially small type PDA, and coarctation. We find low velocity jets in atrial septal defect, PFOs, large VSDs, and venous obstructions, and large communications. Okay, so far I'm sure we have really had a nice time listening to this short brief about Doppler physics. clinical application. It's very important to know about Doppler application when you're doing an echo. Thank you for listening, and it's been nice being with you.